Hello everyone, I am your teacher. My name is Henry Capulong, and in today's lecture we will discuss and prove the monotonic sequence theorem. So the mathematical statement of the monotone convergence theorem, it says that a monotone sequence is convergent only if the sequence is bounded. So in today's topic, we will prove that a bounded monotonic sequence is convergent. But before that, we have some definition of terms that we need to familiarize with, and there are some terminologies na kailangan nating i-discuss at intindihin before proceeding with the formal proof of this theorem. Now, we will begin by defining the limit of a sequence. So the definition says that let L be a real number. The limit of a sequence A sub n is L, written as the limit of A sub n as n approaches infinity is equals to L. If for each epsilon greater than 0, there exists m greater than 0 such that the absolute value of an minus L is less than epsilon whenever n is greater than m. If the limit L of a sequence exists, then the sequence converges to L. If the limit of a sequence does not exist, then the sequence diverges. So we will discuss more of this convergence terminology later in this lecture. But to understand better the definition of the limit of a sequence, so we will take a look at the graph of this of the sequence. So let's say this is the graph, and we have a sequence that is going down or decreasing. So we have here the limit is L, and we have the L plus epsilon on the upper part, and in the lower part of L is L minus epsilon. So epsilon is, we mean by epsilon is, this is just the gap. This is our epsilon, and this is our limit. So epsilon is just very, very tiny na arbitrary number that is both closer to the upper bound and the lower bound is closer to L. So kung mapapansin natin as this sequence approaches decrease and approaches this boundary, then the limit tends towards the L. So this is the definition of the limit. Now we will define what is monotonic. So what is a monotonic sequence? A monotonic sequence is a special kind of sequence in which the successive terms of a sequence are either increasing or decreasing. And that means that the successive term will always be either smaller or greater from the preceding term. So ang ibig sabihin ng monotonic na meron tayong sequence na it tends to increase only or decrease only. So that is what is meant by monotonic. So if we have a sequence an and equals to a1 is less than or equal to a2, and a2 is less than or equal to a3, then we say that this sequence is monotonically increasing. Okay? And if we have an that is with a1 is greater than a2, and a2 is greater than a3, and so on, then we have monotonically decreasing sequence. So medyo mahirap bigkasin. Anyway, we continue and we will examine the graph of monotonic sequence an. So it says here it is increasing if f of f of a plus h is greater than f of a, or and f of a minus h is less than f of a. So sa graph natin ito, if you are looking from left to right, so papaganyan, so makikita natin ng ating graph ay increasing. And we say that x1 is less than x2. So this, makikita natin dito, that's a minus h is less than x equals a, and definitely less than x plus 8. So in this graph, we have a monotonically increasing sequence. Okay. Next graph is we will show the monotonically decreasing sequence. It says here that it is decreasing if an plus 1 is less than or equal to a7. So a function is said to be monotonically decreasing at x equals a if it satisfies f of a plus 8 is less than f of a, and f of a minus 8 is greater than f of a, where 8 is very small value. So as we can see here from left to right, itong graph ng f of x equals e to the negative x is going down. If we will read it from left to right. So obviously, x equals a is smaller than a minus 8, and a plus 8 is smaller than a minus 8. Then we can say that this graph, the sequence is decreasing in this case. So remember, monotonic sequence is either increasing or decreasing. Now, we also mentioned in the theorem that the term bounded. So we will examine what is meant by bounded and convergent also as well. So boundedness, a monotonic sequence is bounded if there is a limit to its values. More specifically, a sequence is bounded above if there is a number m such that no term in the sequence is greater than m. Likewise, it is bounded below if there is a number m such that no term in the sequence is less than m. So mathematically speaking, it is bounded if there exists m that is greater than 0 such that the absolute value of an is less than or equal to m for all small n is an element of big N. Big N is the natural number. And we will explain this more in the succeeding slides. But first, we need to know what is convergent. So if the limit of a sequence exists, then we say that the sequence is convergent. Otherwise, it is divergent. So what does it mean? It means only that if a sequence approaches a value L and equals to L is any constant, then we say that the sequence is convergent. If there is no limit, if the limit does not exist, then we say it is divergent. Now, we can visualize it better if we will take a look at some graphs to show you that what is meant by upper bound, lower bound, and bounded. So upper bound means that a sub n is less than or equal to m. So looking at this graph, we have this graph and we have this m, which is the ceiling of the sequence. They call it sometimes a ceiling or the upper boundary. And we have this an increasing sequence. So kung mapapansin natin, ang ating sequence is increasing but will never cross the arbitrary line m. So meron siyang limit, meron siyang upper limit or upper boundary na hindi niya pwedeng lagpasan. So this is what we call the upper bound. And lower bound means that an is greater than or equal to the small m. So looking at the graph, and sometimes they call it the floor of the sequence. So this is the lower bound of the sequence. It is denoted as a small m, and we have an arbitrary line in which our sequence will never pass. So example, we have a decreasing sequence. So it will continue to decrease, and it will eventually flatten along this line m on the lower part, but it will never cross this arbitrary line m. So we call it a lower bound. So bounded, so this is a combination of these two. So an is greater than or equal to small m, but less than or equal to big M. So mapapansin sa graph na to, we have a sinusoidal wave. Basically, this is a sine wave, and we know from our previous study that sine wave has a limit of sine wave ay meron siyang limit na +1 and the lower limit is -1. So that is a fact from our previous study. And in this case, we have the upper limit m and the lower limit small m, or should we say the boundary m is big M and the boundary small letter m on the lower part. So this is what is meant by bounded. It has an upper boundary and a lower boundary. Okay, now we will proceed since we know the different terminologies that we will be using in this proof. So we have the convergent, we have bounded, we have the epsilon, and the definition of the limit. Now we will proceed with the formal proof of the theorem. So to prove, we need the action of completeness of the real number. So it states that every non-empty set for real numbers that is bounded has at least an upper bound, and also known as the supremum. So let's denote for this discussion, for this topic, let us denote L as the supremum of the sequence of this graph. And we have a sequence an, and this is our boundary m, upper bound m, and it has a supremum of L. So we will begin the proof by assumption. So we assume that an is monotonically increasing, and we further assume that an is convergent, and by convergent it implies that the sequence is bounded. So for this discussion, we will prove this using the sequence an. We will consider it the increasing only. So since the proof is basically the same, the thought process will be the same if you will prove it by the decreasing sequence. So for this discussion, we will prove it by the increasing sequence. So consider set A equals the set of A sub n such that n, small n, is an element of big N. Big N is a natural number. Since it is bounded according to the definition of the supremum, there exists M such that M is an element of real number. And for all n in big N, we have A sub n, which is less than or greater than M. So it is obvious that our sequence an is less than our boundary M. And we claim that, according to the definition of the limit, that the limit an as n approaches infinity is equals L. So rewriting here, claim that limit A sub n equals L, and looking at this graph as our reference. So we have here, we assume this as this is our sequence an. And as per the definition of limit, we have epsilon is greater than 0. So this here, this gap here will be our epsilon, and L minus epsilon, the line here is our L minus epsilon. So obviously we have something here inside that we will later determine that will be important in proving this theorem. So for all n greater than n, then an minus L is less than the epsilon. So if we have this sequence is an, so we will subtract the upper limit, then obviously it will be less than the epsilon. So it is an absolute value. So no matter what we will have here, then the answer will be always positive. So we can write this as L minus A sub n, and it is less than the epsilon. So consider L minus epsilon is less than L. So it is obvious that if L minus epsilon, it is less than L. So as per this diagram, this statement is correct. So since we have this statement, so in between this interval L minus E and L minus E and L, there is still an increasing sequence in between them that we will denote as an. But take note, this an is within this boundary, and it is shaded by yellow. This is, we will consider this as our an. So by definition of supremum, this means that there is an which is an element of our set A. So we denote our sequence an as the element of set A such that an is greater than L, our limit minus E, minus the epsilon. So this here, whatever is the value inside here, whatever the an inside is greater than, if we will subtract the epsilon from the upper for the supremum L. So since an is increasing, so we have L minus n minus epsilon, and an is we have L minus epsilon that is less than an, and an is less than or equal to an, and an is less than or equal to n, and L is less than L plus E. So that is a lot of mathematical statement. But if we will clean these inequalities, so we can understand better. So cleaning the inequality, we observe that n, for all n that is greater than or equal to big N, we obtain L minus epsilon is greater than, is less than an, and an is less than L plus E, which is, this is the definition of our limit in the first part of this slide. Therefore, an minus L, the absolute value of an minus L is less than the epsilon. So since the epsilon is greater than 0, is arbitrary, we have a limit an, that is when as n approaches infinity equals L, thus A is convergent to L. So intuitively, if we will go back with the graph, it will go back to the graph. So intuitively, if the sequence is bounded, so definitely it has a limit. So we are limiting this sequence. It's either we limit is this on the upper side or the lower side. So the sequence will converge to that specific limit that we set. So therefore, we can conclude that the sequence that is bounded and monotonic, then we can say that the sequence is convergent. So that's it. We have proven that the monotone sequence is convergent if it is bounded. Thank you and have a nice day.